lots from. So I welcome you all to this. For our online participants, we see you. Please keep the connection so that we can all enjoy the meeting together. So without further ado, we're going to start the meeting this afternoon, Nigerian time. Today's meeting, I'm sure we already have the schedule. Today's meeting is going to start by the welcome address. Then we do introduction of facilitators and we go into our lectures proper. And I really want to acknowledge everyone who is here. We have esteemed people in our midst, both physically and online already. Among all those that we have Professor Jonathan Dabak, who is ably represented by Professor Titilayo Johnson, and she's going to be taking the welcome charge. We also have Dr. Simeon Omale in the house, is the director of Drosophila Research Lab at the African Center of Excellence in Phytomedicine Research and Development. We also have in our midst Professor Taiwo Alemika, who is the former Deputy Director for the ACE PRD. And we are honored to have you in our midst, SARS and MAS. Right now, we'll be welcoming some people into the high table as we start the ceremony. Professor Titilayo Johnson, please, we would like to have you to come to the high table. She is the PG representative for the Faculty of Basic Medical Sciences at the University of Jos. We'll also be inviting Mr. Yomi Adegboyega, who is the convener of this workshop. Please, can we have you come? Please, can we clap? Can we clap? Online, on-site, please, can we clap for them as they come to the high table? Yes. All right. So without further ado, we are going to begin this workshop. We'll take the welcome address by Professor Titilayo Johnson. Thank you very much.
Thank you very much, Mrs. Adegboyega. So we are all welcome. The Vice Chancellor, the Dean of Faculty of Basic Medical Sciences, all professors seated here, on site, online, and everywhere. All our professors from the University of Jos and professors from Purdue University, USA, and everyone connecting online. We welcome everyone. I am standing here to actually represent the head of Department of Biochemistry, Professor Dabak. He wishes to be here, but is somewhere on another assignment, which is also important. This meeting is jointly organized by JARIS Computational Biology Center in collaboration with the Department of Biochemistry, University of Jos, under the Faculty of Basic Medical Sciences. In fact, the Dean of Faculty was here earlier. She came very early, but she has to be somewhere. And right now she's connecting online. She's here with us online. And let me talk very briefly. Well, I'm sure they will still talk about JARIS, but because I am a witness to the birth of JARIS and a part of it, let me just mention a few things about JARIS, or maybe a brief history of JARIS Computational Biology Center, pioneered by Mr. Abayomi Adegboyega. You know, during the lockdown, he was doing his MSc program in the Department of Biochemistry, University of Jos. And during the lockdown, he happened to be doing some work, searching for drugs against COVID-19. And when we went into computational methods during the time which he laid his hands on some molecular docking research and tried to use some compounds, some FDA-approved antiviral drugs, stopped them against some SARS-CoV-2 proteins and discovered some compounds which coincidentally the same way, and one of the compounds is remdesivir, if you remember very well. Coincidentally, the same week that we discovered that, remdesivir was given emergency use approval, yes, by the FDA. And well, that encouraged him, in fact, it got the attention of the then Deputy VC Academics, and then is currently the VC, the Vice Chancellor of the University of Jos, Professor Tanko Ishaya. And he took interest, and before you know it, he wanted to do some training for a few people, just a few friends, maybe about 20. And we realized that this technique is something that should be exposed to everyone. It will help his research a lot. So we decided to make it open. The first meeting was attended by over 100 people online. And even the Vice Chancellor, the current Vice Chancellor, who was the Deputy VC Academics then, was there seated from the beginning to the end. He gave his full support. The Department of Biochemistry gave full support, and many professors from pharmaceutical sciences, they gave their support. And since then, up till now, I can say that JARIS has trained over 1,000 participants in for different aspects of computer-aided drug design, ranging from molecular docking, molecular dynamic simulation, homology modeling, pharmacophore modeling, ADMET studies, different kinds. And he was our MSc student then, after which he got the opportunity to travel to the US. Currently, he is a PhD student of the Purdue University, and he feels, no, these are new techniques. Let me bring it back home. So that is why we are here. We want to learn some new techniques. For computer-aided drug design, you use the computer. Now we are learning about the Cryo-EM. Is an aspect of structural biology. And then we are going to be using Cryo-VR to enter into a virtual environment to understand how to operate the equipment for Cryo-EM. So it's like hands-on. Many people have been asking, is it hands-on? Yes, it is hands-on, because yesterday I entered the virtual environment and I handled some equipment virtually. I handled equipment. And when I came out of that environment, it was as if I should remain there, because it was a different world. It even took me to one garden, I don't know, it was very interesting. So today we are going to, in fact, throughout this workshop, we are going to be exposed to new things that is going to change our research activities, that is going to take us to a higher level. We have facilitators from Purdue University. We have facilitators from here in the University of Jos. We have a lot of lectures. We have a lot of practical sessions. We have hands-on sessions that we are all going to participate in. So I want to encourage us we are all welcome to be well seated here and listen and enjoy every bit of the workshop. So this is where I will stop. Thank you very much.
All right, thank you so much, Ma, for that opening welcome address. We will be going on. Let me quickly recognize the presence of Professor Jiang, who is from Purdue University, the Structural Biology, Computational Biology, and Biophysics Department of Purdue University, USA. And he's in the house. We recognize you, sir. Thank you very much. We are going to invite Mr. Yomi Adeboyega right now to give a remark, being one of the pioneers of JARIS Computational Biology Center. Please, can we give him a round of applause as he comes?
Okay, thank you very much, everyone, for joining today. It's a great privilege to have everyone in the house and also to have people online already that have joined. I really want to acknowledge our senior professors who are seated in the house already. Professor Lemika, thank you very much, sir. We are really glad to have you. Thank you. And I won't want to say much because of time so that we can continue. I just want to appreciate everyone for attending this meeting and also to appreciate our online audience who are also here already. And we are expecting other people to join online and also on site very soon. Permit me to welcome our professor, Professor Jiang, who is my direct boss at Purdue University. That's the scientific director of the Cryo facility at Purdue University in the United States, who is also my PI. He'll be giving the first lecture on Cryo. That's the cryo electron microscopy, the principles and the application of cryo electron microscopy. Is the first time I'll be learning about cryo. I actually heard from him, I learned from him, and I know nothing about it when I went to the United States, and now I can say I know a little about cryo under his tutelage. So I will introduce him briefly, very brief introduction, and again, I welcome him to take the stage for the lecture as we start the workshop with the opening lecture. So Professor Jiang is a physicist. He has his BSc in physics from Peking University in China. Also, his master's is in biophysics from the Institute of Biophysics, Chinese Academy of Sciences, and his PhD and postdoctoral position in cryo from Professor Wang Chu from Baylor College of Medicine in the United States. So Professor Wen Jiang started as an associate professor, and now is a full professor at Purdue University. He's also the current scientific director of the Purdue Cryo facility in the United States. So we have a very renowned scholar who will be giving us the first lecture on cryo and the applications of cryo to scientific research. So permit me to welcome him as he takes the stage from now. Online, Professor Wen Jiang, the stage is yours. Thank you very much, sir.
Okay, so can you hear me and see my slides? Is everything good? Okay?
Yes, we can hear you and we can see your screen.
Okay, that's great.
Yeah.
Okay, good. So yeah, thank you, Yumi, for the invitation and the introduction. So yeah, so I will just get right into the presentation. So Yumi give me assignment to talk about the cryo its principles and applications. So I next about 40 minutes I will go through that. So okay, well, we started with the purpose for cryo. So we use cryo to solve the structure of, say, viruses and proteins complexes. So then we start to ask, why do we bother to do that? Okay, why structural biology? So I want to start with this diagram. So starting with the human body and the human health. Right, so we all are being troubled by many diseases, especially in recent past several years. The COVID pandemic is really hurting everyone in the world. So, so for us to really understand our body and how diseases work and how to treat it, so we really know enough about ourselves. So anatomy, it is one of the a very fundamental aspect of it, right? So of course, there are many other things to learn. So so I will try to equate the structural biology to the anatomy of macromolecules. So our life fundamentally, right, is a multi-scale hierarchical organization for you know, say organs and cells, and at the bottom is atoms. So many atoms form molecules, small molecules, and then aggregate into polymers and cell organelles and cells, right? So structural biology deal with this bottom level where the individual proteins or multiple proteins form complexes. So we want to understand the structure of this protein and understand how they function. So we understand the function from the structure, the anatomy point of view. Okay. So, and also using the structure to understand how a particular mutations could mess up this structure and the function. So we'll also want to solve the structure so that we give us some environment for us to understand how drug works and also develop new drugs. So to be able to accomplish what we want to achieve with structural biology, one of the very important goal is to obtain the structure at a high enough resolutions. So in this diagram, we try to have a little bit cartoon showing what a resolution means. So in the old days, you know, with the technique still in a pretty early stage, we were limited to the low resolution. Let me see if I can change it to this to say laser pointer. You can see better. So on the left, right, it's very low resolution. Let's say around 20 angstrom, something like that. You will only see each protein as a blob. You only see it over shape. And the resolution become higher and higher, and then you begin to solve see the secondary structural elements like the helices as a little bit elongated rod-like shape. Right, then getting to even higher resolution, then you begin to resolve individual beta strands in the beta sheets. But the real goal is to go beyond full angstrom, in which we call it near atomic resolution. So where we can actually be able to trace the protein backbones and model the side chains. The high resolution, the better. Ideally, probably 3.5, 3 angstrom and higher, so that we get the very reliable atomic models. So that's our goal. So unfortunately, to obtain high resolution is not an easy task. So I have been in cryo-EM for some time. While I entered the field at the time when we were limited to about this area where the cryo-EM was still a blobology time. That time is very few people had confidence that cryo-EM would ever improve to a level that we can kind of resolve the atomic details. Of course, now we all know that cryo-EM is bring a revolution in structural biology, and that's actually the reason why we're here today in this workshop. So in the next half hour, I will to go through some little principal aspect and show what cryo-EM can do. So first to put the structural biology into the big kind of big picture, what kind of method we have. Cryo-EM is not the only method. Actually, before cryo-EM became mainstream, aqueous crystallography and NMR have been around for a few decades. They were really good in solving many high-resolution structures. But one of the challenge for those methods is that, you know, so when the proteins become bigger, it's very hard to grow crystals. And of course, the NMR itself is kind of fundamentally limited to relatively small, say, single domain protein level. So for many proteins, right, so the multiple protein work in complex in the cells. Just like in the society, individuals does not really work well. We need for organization, society to work well. Okay, So the big protein complexes are really hard to be solved by the NMR and accurate crystallography. This is where this cryo-EM, single particle cryo-EM are really good at. So so it turned out that cryo-EM is opposite to crystallography and NMR. So instead of facing challenge with a bigger protein complex, a single particle cryo-EM actually like the big proteins. The bigger, the better, of course, up to a certain limit. Yeah. So so this is where the cryo-EM is located. It's very a powerful method. It can study the targets of very wide range of size, from maybe a few tens of kilodaltons to maybe hundreds of megadaltons, gigadaltons. Okay. So and at a very high resolution now. Okay. So and this diagram put a little bit more quantitative two-dimension kind of a relationship with the other two methods. So in this diagram, you can clearly see, right, in the x axis dimension is the molecular mass of the target, say, and y resolution is the resolution. You can clearly see the cryo-EM is really good with very large targets, but in older days, we were limited to low resolution at the bottom. Okay, so and with the technology advances in recent years, the cryo-EM is faster growing and expanding its territory. So it become a high and high resolution, going to up, and also not only be able to solve large proteins, but also be able to extend the low mass limit to the left very fast. So this is actually what it really kind of pushed the cryo-EM to the mainstream and now become the very hot topic in the structural biology and in biology in general. So just give you a picture of the growth of the cryo-EM. So we thank to the general scientists in the field that we share the structure we solved for many decades. So we have the protein structures archived in the protein databank, the PDB. So this plot in the on the top actually shows the number of the kind of deposited structures over the years. You can see the X-ray with the oldest method. It has still remained the most dominant method. And then cryo-EM is relatively new. It's only began to take off in recent about 15 years here. So, but you are seeing that the cryo-EM is exponentially growing because this y-axis is a log mode. So a linear line indicates is exponentially growing, right? So very fast. And from this trend, it looks like EM is going to overtake X-ray crystallography in a few years in terms of number of structures solved in each year. Okay. So, and also here shows what's the resolution distribution in each year. You see the cryo-EM is very fast growing towards high and high resolution. Majority of the structure now deposited actually full answer and higher. And low resolution is no longer the labor of cryo-EM anymore. So cryo-EM is very powerful method, and everyone who cares about structure probably should look into cryo-EM. Okay, so then here we're going to go into a little bit into the technique itself. Okay, so cryo-EM might sound very kind of daunting, right? But this particular picture, just trying to put into context what I'm really familiar with. We started with our own eyes, right? We using this is for our daily life. So we can see the relatively large things, but we began to see smaller and smaller things. It's becoming harder. So the scientists invented a light microscope, then electron microscope. But this sounds very different. But in terms of the technology, the optics, if we ignore all the glory details, they are very similar. I will show you the diagram in next slides. But here, just want to state that cryo-EM is not that kind of mysterious. So basically, it is just more powerful microscope than our own eye than the light microscope. Of course, it is more powerful in terms of seeing the small things. So in this on the right, it shows that what kind of the best scale and resolution range each of this microscopy can solve. So cryo-EM mostly address the small regime, say from a few nanometer to hundreds of nanometer scale and solve to high resolution. So just for completeness, actually, EM itself is more than just cryo-EM. In the material science, in the EM actually mostly deal with even smaller and high resolution at individual atoms or even the shape of electron clouds. So, but of course, that's beyond the scope of cryo-EM for biology. So this, as I promised in last slide, then TEM, the cryo-EM using the transmission electron microscopy. So it's it's not that mysterious. So here we compare to the optical diagram for a typical light microscope. So everyone probably is very familiar with it. You have a light source, you have the condenser lens to shine light on the sample, then you have objectives and collect the transmitted light, and then you further magnified and record or directly observe using eyeball. So every major component in the optics, we have counterparts in TEM. Of course, the details are quite different. Instead of glass lens, we have magnetic lenses. Instead of light source, we have electron gun to emit electrons. Right, then we never stare at the electrons directly using our eye, always record with a recording device. In older days, using photographic films, now we're using direct electron detectors. So, but if you ignore all the glorious details, cryo-EM, the TEM instrument, it is basically just a more expensive microscope. Okay, so here just quickly show you some the very important milestones and history of TEM and cryo-EM. We want to go through every one of them. I just want to highlight that a few that are directly related to cryo-EM. So, for example, here, Professor Iron Klug got a Nobel Prize in 1982. And then in 2017, we have the three pioneers in cryo-EM got a Nobel Prize for the cryo-EM. Okay, we will show you the picture in next slides. So just for those who are interested in history, okay, so this is what the very first TEM to look like. Okay, invented by Ruska, the very first microscope in 1931. And fast forward a few decades, that this is a Titan Cryos first introduced in around the year 2008, was what really kind of pushed the cryo-EM to what we are enjoying right now. It's mostly due to the technology refinement through this decades. Now in the new most powerful Titan Cryos TEMs, we have a much clean vacuum. So allow us to collect a lot of images for a long time, multiple days, instead of being contaminated within hours. So it has a much better electron, the condensers to provide the best quality beam and the quality of the images. And then the other more convenient features that it allows multiple sample grid being loaded in one go, and then we can find the best grid to image for a long time with computer automation, so that we can collect enough images to allow us to average and improve the signal-to-noise ratio, which I will highlight, emphasize later again on the signal-to-noise ratio. Okay. So as I promised that in Cryo throughout the development, okay, we have many very important milestones to be accomplished and by the entire field. But the effort was mostly recognized as the two examples here, the two Nobel Prizes, Professor Ironklug in MRC, for probably the very first demonstration that indeed it is possible to recover 3D information from 2D projection images. Then later in 2017, it's more specialized for cryo-EM. So is that the three pioneers demonstrated that the biologic sample can be preserved in the hydrated state and it can go to high resolution and with pretty kind of advanced 3D reconstruction method. We won't go into details of individuals' achievement, but it's a few relevant aspects in next few slides. So instead of going through all the glorious technical aspect, this just gives you a very high level kind of a diagram of what a cryo-EM really is. So cryo-EM is abbreviation. Just from itself, cryo means low temperature, EM is just microscopy. But a cryo-EM is actually more than just taking pictures. So as shown in this left diagram, so the entire cryo-EM workflow actually consists first, you have prepared good samples and load into the column, and then collect a lot of images. If we ignore all the details, basically you can think about electron going through the sample and then accumulate the information. So the 2D images are the projections, not the surface scans like SEM or FM, other surface scanning instrument. Because this projection and the information in the 2D images actually encode the 3D information, although it was collapsed and lost. And this is where the next stage, computational reconstruction, is very important. We have to combine many images that represent different direction of the projections to recover the 3D information. This is equivalent to what we are using our 2 eyes for every second. We need, using 2 eyes, look at the same object from different angle, develop a sense of 3D. But a 3D cryo-EM actually go to a much more extreme. We want to be able to see the same object, target, protein, from all angles, 360s, and all angles. So this is, if we ignore a lot of this technical details, this principle is pretty similar, especially similar to the CT scan that in the hospital. There's mathematics, the radon transform, and then the reconstruction from the radon transform is actually very similar. But the cryo-EM is very challenged, mostly due to the fact that the images are extremely noisy. Okay, this is actually 2 examples show how they look like when the image under the typical cryo-EM conditions, say 480 kD purity and for relatively smaller 124 kD purity, how they look like. Okay, so you immediately see they're very noisy and pretty hard to come out just from our own intuition. So this is where the powerful computational programs, algorithms are essential to recover the information by combining numerous of this kind of individual particle images. So we won't go to too much of the details, but later in this workshop that you will go through some of the practical aspect, learn how to go from 2D images and to obtain 3D structures. Okay, so one of these critical stage, probably still the bottleneck, is how to prepare the best sample for you to load into microscope and an image. So this is the one that's a very essential step. This is where the cryo part of cryo-EM. So in the mid 80s, this task was kind of solved by Professor Jack Dubuchet and many other investigators in the field. So it turns out actually pretty straightforward. In retrospect, it's very simple, but it took us some time in those days to figure it out. So because before that, the biologic sample were mostly stained with heavy metal and fixed, and so that it can survive in the vacuum and then have enough contrast. But with the cryo plant freezing method developed by Professor Jack Dubuchet, right? So as shown by this classic milestone pictures of adenovirus published on Nature in 1984, you can see that the viruses itself entirely hydrated in water environment without any heavy metal stain. You can see the particles, you can see even the fine details in each of the particles. So that really serve as a kind of the day that indeed cryo-EM, the plant freezing, and indeed can preserve the particle to the high resolution and allow faithful kind of reconstruction of the 3D structures. So one of these common myths for the plant freezing for people who are not in this cryo field is that now, in our daily life, in our previous education, very often we're afraid of freezing. We all probably afraid that in the cold winter, in very cold places, when we're frozen, and then our body will be damaged, right? So, but that indeed was a bottleneck at that time. But of course, then the field figured out that depending on the speed of freezing, the water actually has very complex behavior. In a typical our daily life, when we freeze the water very slowly, right, we will form the ice, we call the hexagonal crystalline ice, that indeed is very damaging. But if we freeze the water really fast, so fast that the water molecules do not have enough time to crystallize, basically just snapshot the liquid like the loosely kind of form the hydrogen bond network in the liquid water, just immobilize that state. Then this state called a vitreous ice, or the other term amorphous ice or glassy ice. The take-home message is that this vitreous ice is good. It preserves the protein and is in native hydrated state without damaging the particles. And that is what we use in the cryo-EM. Okay. So on the left, on the right, basically says that how do we know what kind of ice we have obtained? Turns out this is pretty straightforward in cryo-EM. If you look at a particular sample, for example, using the electron diffraction mode, if it's a hexagonal ice, you see the nice diffraction patterns, like the diffraction pattern you would see in the aqueous crystallography of the good crystals. If it's the other kind of intermediate stage of cubic ice, you see the rings instead of spots. But if it's a vitreous ice, you do not see any spots or rings. It's just non-crystalline, just amorphous. So that would be the ice that you aim for. So once you obtained a lot of nice images, then the task of 3D reconstruction will actually combine multiple images and then recover a nice 3D structure of the 2D projection images. So we won't go into too much of details in this, it's very involved. So just a very brief kind of overview of what the typical concept is this. Let's say on this, in this diagram on the right, let's say this is a 3D structure we want to recover. Of course, we have no clue what it is in advances, right? So, but what the data we obtain is a lot of the 2D projection image, like shown in this cartoon, right? The side view, front view, and top view, other views. Then we will, using a series for image analysis steps and recover the 3D. And depending on the method software used, the details might vary a little bit, but in general, it is consistent, is that you need to somehow, find the relative view angle between the different projections. then allow you to kind of combine coherently instead of randomly. So many of this process, especially in the early research, even still now. So we utilize 2D Fourier transform, 3D Fourier transforms all the time. So some of the mathematics involved, but we won't go into too much detail here today. If you are interested, you're welcome to look into more details. There's a lot of learning material on the internet nowadays. So what type of sample are suitable for cryo-EM? Okay, turns out cryo-EM is very versatile tool. So you can deal with many different type of samples, say starting from the kind of more crystalline like 2D crystals, and then down to the orders 1D crystals, we call it 1D helical filament or tubes. All the objects that without any long range order, like this, we call it single particles, they can be further divided into general groups. One is the large particle with high symmetry, like the icosahedral viruses. And then the other group that without a symmetry. Okay. So as I emphasized earlier on that the number one kind of enemy in cryo-EM is the very low signal-to-noise ratio due to the rich damage of electrons to the biological sample when you collect data. The high energy electrons accumulate a signal, but at the same time damage the sample. So that is a physical limit. We still have not figured out how to overcome it yet. So that limit the amount of radiation or dose we can put on a sample before it's damaged enough and become a meaningless. So when you have the crystalline order or large mass or symmetry, that's really helpful because that helps to enhance the signal-to-noise ratio. It's not surprising that 2D crystals were first targeted, solved to high resolution even in the 80s. And for the 1D crystal in the early this century. And of course, for the more challenging amyloids, they're only being solved in recent years. So then I'm going to show you some examples of the 2D crystals first. So Professor Richard Henderson and his colleague actually demonstrated it very early on in 1975, even before cryo-EM, the cryopod was established. He already demonstrated with one 2D crystal sample called bacterial Dobson or purple membrane. It's a membrane protein that in the cell membrane for halophilic bacteria, and naturally forming a very well-ordered 2D crystal patches in the cell. Basically, the cells are swimming around carrying well-ordered 2D crystals in the cell membrane. It's kind of interesting picture. So those 2D crystals in purple membrane were imaged and then recombined into 3D models in the 75. The 7 transmembrane helices model were proposed based on the EM data, and that was the very first membrane protein structure by any method. So yeah, so then in more recent years, actually this electron crystallography of 2D crystals has been extended to 3D crystals, but limited to, but it's specific for the small crystals, or depending on who you are, you might call it nanocrystals or might call it microcrystals. But the idea is that the crystals must be very small because electrons have a very limited penetrating power. If it's too large, especially in the Z dimension, if it's too large, then electron want to go through, it won't work for EM. So in this particular diagram, it shows this tiny invisible dots, almost invisible, right? Those are the tiny crystals that cryo-EM would want. You want to be less than 0.5 micrometer in thick, but in XY dimension, it can be any size. Okay, for those, actually turned out that these tiny crystals were considered useless for X-ray crystallography. It turns out to be best sample for the electron crystallography, or there's a nickname called micro-ED, to go to very high resolution. So it can be kind of a very powerful method in application, especially in for the chemists study the drugs, the compounds, how their structure look like, okay, from the drug powders directly. So then here shows that a few examples of helical structures. It turns out that this biopolymers that consist of multiple copies of the units along one dimension, right? So these are pretty common. Starting from the most familiar cases is double-stranded DNA, the double helix, shown on the left. You probably all know that the actin, microtubule, those are cytoskeleton proteins from the 1D crystals, and the bacteria using the flagella, the helical flagella to swim around. Then your classic textbook T4 phages with the tail. Turns out that the phage tail, T4 tail, was the very early target of 3D EM, even back in the 60s. So then we have the more recent years, we've extended this structure study to some very kind of significant set of target is the protein amyloids that are involved in most of the neurodegenerative diseases and becoming a real medical issues as the population is aging. In the rightmost is actually one example of enzymes from the polymers. So it turns out that actually many of these enzymes that will form this high order polymers that as one way to regulate its function. So that's very interesting, a new mode of regulation that is not yet written in the textbook yet. So, but what it really has pushed the cryo-EM to the mainstream is the called single particle cryo-EM. So, so here are just a few statements about what the benefits of single particle cryo-EM can bring. Okay, so this is kind of a statement called crystallography without a crystal. Okay, so this is what statement trying to bring relate single particle cryo-EM to the more familiar crystallography method. So instead of let nature or your luck to order the individual proteins into physical crystals, we in turn actually in cryo-EM we use some computer method to find the view angles, the positions, basically virtually align the individual proteins into order. So basically kind of underquote crystallography without crystals. So because cryo-EM take pictures, images, they provide both the called amplitude information and the phasing information. We don't have the phasing problem that accurate crystallography faced. So that is immediately is a winning kind of advantage from the images. So of course the other aspect is pretty kind of intuitive, right? So the cryo-EM freezes the sample, and this fast freezing actually preserve the sample in the frozen hydrated state. It's more physiologically relevant state than maybe some arbitrary and pH or salt or other additive conditions. So, but I would emphasize that although we enjoying the single particle cryo-EM in recent years, right? But we do need to kind of remember that single particle cryo-EM is fundamentally challenged. Very challenging. Okay, that's why it took several decades to go from the early days in a very frustrating period to nowadays everyone enjoying that. The real challenge is actually you can go through all these challenges, but all of them can be probably boiled down to this statement here. Due to the relatively small mass of single particles and very low scattering, and then low signal-to-noise ratio. So that is the fundamental limit. So in this slide is my personal view on this little bit of history of cryo-EM, where they are and why, where will be next. So here shows the three milestones we already accomplished. We figured out how to plunge freeze the samples and preserve the sample in the liquid nitrogen temperature. Then we have this a very powerful electron microscope that Titan creates. Then the last piece of the overall pipeline we need is the direct electron detectors that will have the best recording quality per electrons. So this combined allow us to solve the structures that we can deal with so far. Say, for example, very early on, we don't even need plunge freezing, as shown by the purple membrane. The 2D crystal itself has a very large amount of signal-to-noise ratio. So then we could solve it early on. The large hydroviruses is very large in mass. We only need, Titan Cryos with all the photograph film, CCD recording, and be able to solve the high resolution. But the relative small protein complexes, a few hundred kDs, do need the last piece is the direct electron detectors combined with the other two as a system, not just the camera itself. Be able to collectively have the enough signal-to-noise ratio to allow us to solve the protein complexes. But in the processes, I marked that only have discrete conformations, because many of the protein complexes actually involve very serious dynamic conformations. Just like what we are living in every day, we are moving around. Individual proteins also need to go through multiple conformations. Very often it's continuous varying conformations to fulfill the functions. So this actually turns out to be an enemy of structural biology, where we don't, because we don't have identical copies to average with. So we're still in the field, we're still searching for the next method improvement, how to enhance the signal-to-noise ratio further so that we can deal with the remaining challenge in the single part cryo-EM. So, this is one thought, maybe the CC correctors, or maybe the best laser-based faceplate. See, this tool might sound very kind of mysterious to you, but that's fine. But if you're curious, you can kind of look it up. You probably might see a lot of this from the internet. So the take-home message is that cryo-EM has accomplished a huge kind of amount of the targets, but still we have something to do. Okay, but hopefully with new workforce and new talents, new ideas hopefully from one of you can help us to push the cryo-EM to even overcome the very last major challenge in the field. So so then this shows that the kind of early milestone of a single part cryo-EM about 10 years ago, where that is what pushed cryo-EM beyond just the experts in the EM field and to the general structural biology, even well beyond structural biology. It is probably signaled by the structure of the trip channel shown on the left. Trip channel are a large family of transmembrane proteins. Was really hard to solve using crystallography without much of a success after probably more than a decade, 2 decades of intense effort by the entire field. But then Professor Yifan Chen's group solved this trip channel in around 2013. That really got everybody excited. Then after that, the rest was amazing. The resolution kept growing, say quickly to 2.2 angstrom. Then actually a few years later, now it actually reached a true atomic resolution, as shown here, 1.2, 1.2 angstrom of the Eber-13, the model system. Well, in the structure, you can see individual atoms. That's a true atomic resolution, less than 1.5 angstrom, less than the bond length of the carbon-carbon single bonds. So cryo-EM, the structure is not only useful for the basic science, but also very useful for the drug based structure-based drug design. As shown in this picture, right? So depending on the resolution you can achieve, even at a relatively low resolution, right? You can actually begin to see the general location of the ligand, right? And the shape of the ligand. Or if you're lucky, get a very high resolution, you can see kind of an accurate model, individual atom position allow you to guide the optimization of your ligand to improve the design. So here just one slide to focus on this remaining challenge in the dynamic state we already kind of mentioned. That in this cartoon showing is that on the left, let's say in the conformational space, if only one very sharp peak or multiple sharp peaks, small numbers, few to 10 probably okay. And in Cryo right now, we have a very powerful computation method and enough signal to allow to solve them. But what really hard is this, the bottom, it's called a continuous dynamics, where you have distribution instead of small number peaks, then that is really hard. So you can probably picture this problem, abstract problem, into something shown on here on the top right, where this is actually the very first high-speed photography of a horse, where that time there was a debate. Would the horse ever actually have all 4 feet off the ground or not? That time, our human brain, our eye were not fast enough to capture that moment. So this is, was the very first photography to show that solve that issue. So the relevance to the cryo-EM dynamic problem is this. So each of the protein probably related to the host, and there is kind of moving in right in going through the dynamic state, and it's a huge number of changes, and we're still searching for the best method to solve this challenge. We probably will have all the different methods, either from the typical molecular biology, genetic, biochemical approach screenings to force the conditions to maybe to nicer distributions, or more ideally, we should embrace the dynamics and probably develop some computational sorting method, and probably more importantly, to improve the signal-to-noise ratio so that we do have enough signal to detect the subtle differences between different conformations. So that will be remaining challenge, and really I need new ideas and new fresh minds and talents to help us to solve this challenge. Okay, so that is what we have now. But here I'm going to show you that what is exciting future where it is. So far we talk about these called in vitro or isolated systems, where we actually intentionally break the cells and separate our target from the cells. They are very useful, but we always want to go back to the cell contact, go back to the cells and tissues and organs, look at the structures in situ, where the true environment. So due to the technology limit in the past, we couldn't only dream about it, but couldn't do anything. But with the modern technology measures available, now we are faster progressing towards this area of study. We have the fantastic new instruments. We can cut the cells or tissues into thin sections and make it thin enough. We can obtain this tomography data. We'll tilt the sample to a different angle to collect the projection views, images from all the different views, then go through computational analysis to get the structures. So this is considered very challenging, but we begin to have success that this actually might be doable. For example, shown here, the left is a technology demonstration using just isolated single particles. We show that tomography and then averaging can indeed get very high resolution as shown here. 3 angstrom and HIV GAC protein and 1.8 angstrom epiferity. Of course, those are in vitro, but how about the actual in situ, in vivo? structure. This is showing one example where the ribosome in the cell sections can be imaged and average and obtain 3.5 angstrom with all these details that you expect at that resolution. This is extremely exciting accomplishment. This probably shows that it's feasible, but we do need still need a lot of technical refinement to make this method more friendly, accessible to everybody, not just a few pioneer hands, because it's really actually technology challenge, and also instrument are pretty expensive as well. But we do see the hope that it will probably become the future in the coming years. So so with that, I would just kind of end our presentation with just a very brief introduction to what we do in MATLAB at Purdue. So as Yomi introduced, I have been in cryo for a long time. I was original physicist, so my interest is in the methods and application and their interplay. So everything we do is involved in the cryo. We applied to different types of samples, proteins, viruses, and amyloids, and other nanoparticles. And then we are interested in methods. So how to improve the sample preparation and other related, and also the instrument image analysis aspect. So we won't go into too much details. Just show that throughout the years, we have solved many structures, and they just selected examples of those categorized in, say, viruses, the high symmetric, the capsid structures, and this whole virus structures beyond this symmetric a component, including the tails and other non-symmetric components. Then we also apply to different protein complexes, and more recently in the protein amyloid structures. So as shown here. Then actually my student Kadir later will actually present a short talk on the cryo study for amyloid structures. So with that, I would like to thank everyone in my group who are being working hard on the cryo applications and methods, and my collaborators throughout the years on the different projects, and the fundings from different agencies, the NIH institutes, and the local funding sources. And our cryo facility is a wonderful facility that with state-of-the-art instruments, where our technical director, Thomas Close, will give you a much deeper overview in the next presentations. So with that, I will thank you for your attention. I'll be happy to answer questions if you do have. So thank you.
All right, that was an awesome lecture given by our professor, Professor Wang Jiang from Purdue University. We appreciate you, sir, for sharing your knowledge and your expertise, and as well as your time with us. We really appreciate you. We'll be going on to take some questions now. For want of time, we'll be taking just one question from the online participants and one question for the participants on site. So please, if you have a question, for those on site, please just raise your hand. But I already have a question here in the chat box from the online participants. The question says, like in X-ray crystallography, we rotate the crystal, the data to collect the images. How do we collect the data in case of cryo-EM?
Yeah, so okay, so I think that Thomas probably will show much more details. So we apply a very small amount of sample, a few microliters on a small EM grid, about a 3 millimeter metal mesh. Then we plot most of the solution will leave about a very thin layer, probably total mass volume about a nanoliter material on the grid. So the thickness is about maybe 20, 30 nanometer thick, depending on how large your target is. Then I will load it into the microscope, and then just move around and take a lot of pictures. Each picture probably across about half a micrometer in size in XY dimension, then we'll accumulate just a lot of the thousands, tens of thousands images, giving us maybe a few 100,000 to a few million particles. Then go there from there, then using computer method, extract each of the particles, then determine the views and average them. So that's how we obtain the data and solve it. So quite different from the X-ray crystallography.
All right, thank you so much, Professor. Do we have anybody on site with a question? Anybody? All right, then, I guess that would be it. I really appreciate you, Professor Jiang, again, for your time and for the knowledge that you have passed on to us graciously. And thank you for the collaboration that you have offered to give us for this workshop. We appreciate it. Please, can we clap for him again?
Thank you, it's my pleasure.
All right, thank you. All right, so we'll be moving on to the next lecture. That's lecture 2 and practical 1, which is overview of cryo-EM technique workflow and introduction to instrumentation. This will be taken by Dr. Thomas Close, still from structural biology for the